Hey, today we will study cycloatomic spectra with Frobenius lift. So these are cycloatomic spectra where the Frobenius map does not just come from a map into Tate, but it actually factors through a map into homotopy fixed points. And in that case, we will deduce a much more powerful formula for TC, a much more explicit formula for TC. So examples that we will study are these cycloatomic spectra X triv, but a slightly more exciting example is going to be given by spherical group rings. So we will see how to apply, how to get a Frobenius lift on those and how to compute their TC. I'm Achim Krause from Mathematics Münster. So first of all, we need to define what we mean by a Frobenius lift. So a cycloatomic spectrum with Frobenius lift, and we will focus on the kind of p-local setting here where we just look at a Frobenius for a single prime, but of course there's also a corresponding kind of global version. So let's say a p-cycloatomic spectrum with Frobenius lift is a p-cycloatomic spectrum X with a T or S1 equivariant factorization of the Frobenius. So the Frobenius goes to X upper Tate CP, and we want this to actually factor through homotopy fixed points. Right? There's this kind of trivial or canonical map from homotopy fixed points to Tate, and so we're asking for the Frobenius phi p to factor through a map psi p. And as with the Frobenius, that map also should be T equivariant. So we want this diagram to be a factorization in like the T equivariant world. And we already saw one example of this. Namely, if you recall, we saw how to put on any spectrum a trivial cycloatomic structure, where the T action is the trivial one, and the map, the Frobenius, was defined as a composite like this. So X triv admits a Frobenius lift since we defined phi p as composite like this, where this was the canonical map you get if you took a trivial CP action and you take homotopy fixed points. There's always a map like this. And here we continue with the canonical map, right? This was the definition of the Frobenius, the cycloatomic Frobenius for this X triv cycloatomic structure. And so this map here would be our psi p in that case. Right, and I guess another description we gave for this is simply if you write X as map from sigma infinity plus of the point to X, from the sphere to X, and this guy as map from sigma infinity plus BCP to X, then this map here is simply precomposing with the canonical map from BCP to the point. Right. So given such a Frobenius lift, we can actually reformulate the formula for TC in terms of this equalizer between the Frobenius and the canonical map from like T, like from TC minus to TP. And how do we do that? Well, so if X has a Frobenius lift then this map phi from Tc minus, i.e. homotopy fixed points, to Tp, i.e. the Tate construction, factors namely how? Well, so remember how this map works, right? So this map worked by taking the Frobenius from x to x upper Tate Cp, and then applying homotopy fixed points with respect to the T action to both sides. And due to the way T acts on this, right, this was the residual action obtained from identifying, like you had a T action on the whole thing, then you took Tate, so you have T modulo this subgroup Cp acting, but S1 modulo a cyclic subgroup is still isomorphic to S1. So this T here, you should maybe think of this in this context as like T mod Cp. And we had this Tate orbit lemma that tells you that this guy is actually equivalent to Tate T. Under the assumption, sorry, I should have said that, under the assumption that X is P-complete. So we will impose that multiple times in this lecture. So otherwise, this is only an equivalence after T-completion, P-completion. Right, so this was how the map phi worked. And since this map up here is phi p, and then you apply the functor homotopy fixed points, this factorization also gives you a map to x upper hcp, and then upper ht with respect to the residual action. Right, where this map here is like phi p upper psi p upper ht. And similarly to what goes on here, this guy here, where you take fixed points and then you take fixed points with respect to the residual action, that's the same as taking fixed points with respect to the whole T action. Right? And this map here, that's this map TRIF. Right? So this is like TRIF upper HT. So this is again the trivial or canonical map from HT to Tate T. I guess in this context we called this can, but same thing. There's a canonical or trivial map from homotopy fixed points to Tate, and that's the map that occurs here. Okay, so we see that the Frobenius that appears in the definition of Tc, here it actually factors through an endomorphism of Tc minus. And in particular, the map phi minus can from x upper ht to x upper Tate T. This factors as the composite x upper ht, x upper ht. Here we take this map here, which maybe I should call psi now, this endomorphism psi minus the identity. And then here we just take can. Right? Because, I mean, we can factor can through an endomorphism followed by can, namely the identity. And we can factor phi through an endomorphism followed by can, namely this psi. And so you get this factorization. Okay, and so Tc was defined as fiber of this map, right, as the equalizer of phi and can. So you should expect that from this formula, we maybe get to squeeze out a little more information about Tc. So let me do that out. All right, so here's a theorem. So in the setting we're in, so X is a P complete bounded below P cyclotomic spectrum with Frobenius lift. Then we have a pullback diagram where we have TCX here. And then, this is the crazy part, we just have 2 copies of X here and homotopy orbits, shifted homotopy orbits with respect to the T action on X. And here, this map is psi p minus the identity. So what do I mean by psi p? Psi p was a map from X to homotopy fixed points on X. I can forget down to X, right? I always have a map from homotopy fixed points to X. And I'm abusively calling the composite still psi p, because one way to think about maps into homotopy fixed points is that a map from a spectrum into something like homotopy fixed points with respect to a G action on a spectrum X is the same as just a map into X which is equivariant with respect to the trivial action on the domain and the given action on X. Right? So here I'm thinking about the map psi p from X to X upper HCP simply as kind of an equivariant map from X to X. And so I'm just forgetting some information here in looking at this as an endomorphism. Right. And I guess this map here is similarly obtained from the map you have from sigma of homotopy orbits to homotopy fixed points, the norm map for the Lie group T, S1. And then the forgetful map from X upper HT down to X. All right, so maybe let's call this transfer. Right? This is like the norm. Okay. So, and the claim is this is a pullback. So what's the idea? Let me give you a proof sketch, because there's one ingredient which I'm not really going to prove. But the first idea is TC was defined as a homotopy fiber, right? As a fiber of this map phi minus can. So first of all, let's try to involve this factorization. So the first observation we make is TC was obtained as fiber of this map, so in other words, as pullback of this map. Right? So this is a pullback diagram. And now we can factor the map down here through this psi minus identity and the map can here. And similarly, we can factor this whole pullback diagram, because what's the pullback here? Well, that's the fiber of can, but can, or like Tate, was defined as the cofiber of the norm map, right? So you get a diagram where here you have the domain of the norm map, sigma lower ht, and here you have the norm. And so this diagram here is a pullback by definition of Tate. And now if you think about it, if you have 2 pasted squares like this, and the right-hand side square is a pullback, and the whole thing is a pullback, then the left-hand side guy is a pullback as well. You can get that from universal properties, but in this stable setting, you can even get it from the fact that a square is a pullback if and only if the map, the horizontal map on the fibers of the vertical maps is an equivalence. right? So this being a pullback means the map between fibers of these guys is an equivalence, and the whole thing being a pullback also tells you that the fiber of this agrees with the fiber of this. So in particular, the fiber of this agrees with the fiber of this. So in any case, this shows that this is a pullback. And this square here, that already looks a lot like this, right? Except here we have x upper ht, and here we just have x. And of course, what we're claiming here is that another diagram is a pullback, right? So you can extend this diagram here by just putting psi p minus identity, as I did up here, and the vertical maps are just the forgetful maps from homotopy fixed points to the underlying spectrum. And the claim is that since x is p-complete, so it's not a general statement, but under this assumption that x is p-complete, this diagram here is a pullback as well. And I don't want to do that in detail. If you want to see the details, this is done in section 4 of the Nikolaus-Scholze paper on topological cyclic homology. But the idea is roughly, think about the case where x is just Eilenberg-MacLane, say the p-adix, and the t-action is trivial. In that case, up here, you're seeing something like the cohomology of Cp infinity. And down here, you're just seeing the p-adix, sort of the degree 0 cohomology of Cp infinity. And what goes into this being a pullback is the observation that this map psi here on the cohomology of Cp infinity in that case, it's kind of on all the higher degrees, it's just multiplication by a non-trivial power of p. And so this psi minus identity is an isomorphism on all higher degree cohomology of Cp infinity in that case. And there you also see why you need this to be p-complete, right? That wouldn't work over, say, integer coefficients. Right. Let me not go into that further, but it's having to do with this kind of thought that I just sketched. Right, so this is a pullback as well, and then you can just paste pullback diagrams to get what I wrote up here. And one cool corollary that we can already kind of harvest from this is the following. So we saw that for any spectrum, you can put this trivial cyclotomic structure on it, where the T action is trivial and the Frobenius is this composition. And we saw a couple of boards earlier that actually comes more or less by construction with Frobenius lifts. So we can apply that formula there. And the claim is, if you take a p-complete bounded below spectrum, and you put this trivial cyclotomic structure on it, then TC triv actually has this very nice description as just a copy of x that splits off, and then x smashed with or tensored with a very specific spectrum, namely with the fiber of the map from homotopy orbits of S to S. Right, and this map here, that's this thing I call transfer over there, just for the spectrum S. Right, so it's a composite of the norm that arises in defining the Tate construction, and simply the forgetful map from homotopy fixed points down to the underlying spectrum. Right. So somehow you can kind of see how this arises from this, namely I guess I'm. So the idea is that over here, in this TRIF case, you will see that the psi p is the identity. And so in that case, the lower map in your pullback is 0. And so the left-hand x just splits off. And the other summand is the fiber of the transfer here. But in the case of the trivial T action, that is actually just obtained from this map for S. And so I want to pose the details as an exercise. I think this is, again, a very good way to develop some intuition for what's going on here. So just try to check this using the theorem over here. And one final thing I want to remark. So this mysterious spectrum over here actually has kind of a cool name. So this is the suspension of what's usually called Cp infinity minus 1. And this is kind of funny. One way to think about this is as a certain Thom spectrum over Cp infinity. The notation comes from the fact that for positive n, there is a spectrum called Cp, or even a space in that case, called Cp infinity n, which you get by taking Cp infinity and truncating away the 2n minus 2 skeleton. So you get something with cells in every even degree starting with degree 2n. That's what people call Cp infinity n. And then Cp infinity minus 1 kind of extrapolates this to negative numbers. So this is a spectrum. If you think about it, if you desuspend this once, think about what this fiber gives you. This will be a spectrum with cells in every even degree starting with degree minus 2. And this is usually called Cp infinity minus 1. So it's kind of a funny notation, but this is a very classical object that people have studied in stable homotopic theory. All right. So now our next goal is to explore a slightly less trivial example of cycloatomic spectra with Frobenius lifts. And that's the example of spherical group rings. So for a E1 group G, so let G be an E1 group in the infinity category of spaces. And remember that there was this something that's classically called the recognition theorem, which tells you that there's an equivalence between E1 groups in spaces and pointed connected spaces. And the equivalence was through the loops functor. So if you take a pointed connected space, then loops of it is going to be an E1 group. And the other way around, you have the bar construction. You have the functor B, which takes a group to, well, a space, which is a D-looping of it. So equivalently, it's kind of what you should keep in mind as a source of examples for this. Equivalently, you can think of G as loops of a space Y here. Right? But of course, you can also just take a discrete group, and that will give you an E1 group. In that case, the Y here will be the classifying space, BG. I guess in general, this Y here is going to be BG. Take topological groups as well, all manner of things. What do I mean by group ring? Well, so we write S adjoint G. It's funny kind of group ring notation for the spectrum sigma infinity plus G. Right? And why is this notation justified? Well, if you think about it, if you plug in a discrete group G, then this sigma infinity, then G as a space is just going to be a disjoint union of points. And so sigma infinity plus is going to be a sum of sigma infinity plus of the point, so a sum of Sear spectra. Right? So in the case where G is discrete, this is a sum of copies of S, one summoned for each element of G. So this kind of looks like a free module over S generated by the elements of G. And so that's exactly what you do when you take group rings over ordinary rings, right? You take a free module on all the generators of G, and then you put a suitable group structure on it, like a suitable ring structure on it, coming from the group multiplication. And of course, the same thing happens here as well. Sigma infinity plus is symmetric monoidal from spaces to spectra. And so if you take an E1 group, in particular an E1 monoid in spaces, you will get an E1 ring in spectra, or E1 algebra, or whatever you want to call it. Right. So this justifies this notation. I think this is a very nice conceptual way of thinking about it. And in particular, we can take THH of such a thing. And one thing I will say here, so why is it interesting to study THH and TC of these funny rings? Well, the point is that through trace methods, this allows you to compute K-theory of these funny rings in many examples. And what's the relationship, like why is that interesting? Well, it turns out K-theory of such a guy, of S adjoint loops Y, that's what's called A-theory of the space Y. And that plays an important role in geometric topology. And so through understanding TC of these guys, you can get control over A-theory of their D-looping. But I'll not go into that today. I just wanted to leave it here as like a motivation. Right. So if we want to compute TC, then first of all, we have to think about THH. And there's a nice formula for this, which tells you that, again, THH of such a guy is going to be a suspension spectrum. And you have this funny appearance of the free loop space. Right? So when I write omega, then I mean the space of loops based at the base point. And when I write L, then I really mean the free loop space, meaning it's just the space of maps from S1 into BG, and you don't care about where the base point of S1 goes to. Right. So how does that work? Well, first of all, why should this be a suspension spectrum? Well, that part is easy. So THH was defined via this cyclic bar construction. And since sigma infinity plus is symmetric monoidal and commutes with colimits, you can pull it out of the cyclic bar construction. And you get that this is sigma infinity plus of the colimit of the cyclic bar construction formed just on the space G, on the E1 monoid in spaces G. So we want to compare this to this free loop space over here. And here's a fun little other way of thinking about this, which is, so we compare the whole cyclic object, right? This was this simplicial object with this kind of extra structure. So we can compare this whole cyclic object with the cyclic object, which is kind of like a cyclic nerve of BG. So what do I mean by that? Well, it's given by taking functors from something which I'm going to temporarily just write S bullet, no relationship to the infinity category of spaces. I guess the S is here because it's sort of like a circle. So this is going to be a certain one category, and we can map this into the infinity groupoid BG. And what's S bullet? Well, Sn, and remember for cyclic objects the indexing was kind of funny. It starts instead of with 0 as for simplicial objects, it starts with 1. So the 0 simplices are going to come from S1. And what's Sn? Well, this is going to be the category with objects 0, 1, ... n minus 1, n. Think of them as kind of like a circle. And then it's going to be generated by morphisms from one guy to the next. Right? So in particular, there's going to be a composite all the way around, and we're not asking for this to be identity. Right? So one thing one can check, for example, is that here the endomorphisms in this category I just described, the endomorphisms of any single object are really just free on one generator. They're like the natural numbers, the monoid of natural numbers. Right. So this is a perfectly fine category, and I'm not going to do this here, but you can check that this is kind of like a co-cyclic object, this S bullet, and so taking functors out of it is going to give you cyclic objects. Similar to how mapping out of like these linear ordered sets gives you simplicial objects. Right. So this defines a cyclic object, and you could hope that this just gives you the cyclic bar construction. There is a subtlety here though, right? Which is that this groupoid here, right? This is like the functor category, but since your target is a groupoid, this is going to be a groupoid as well, because all the natural transformations are going to be invertible. This infinity groupoid here, for a fixed n, it's not what you would think of at the first glance, right? Fun of Sn into Bg is not simply G cross n, which is the thing you have in the corresponding degree here. Remember, the indexing is funny, it starts with 1. Right, so why is it not this? Well, to give a functor from this thing to Bg, you're sending every, like Bg, think of Bg as a category with one object, with endomorphisms given by G, then you're sending every object to the one object, and you're sending every morphism to some element of G. So the data of a functor is a point in G cross n. But then you also have natural transformations, right? You're not fixing these points. So you'll have natural isomorphisms that just do something on the points here. And so this space, this infinity groupoid, has kind of a funny description where you take homotopy orbits under an action by another copy of G cross n. Right? Because giving a natural isomorphism between two such functors just corresponds to picking some isomorphism from the one object to the one object at each of the points of my diagram. But the action here is not the free one, right? If you take such a diagram and you modify it by isomorphisms on each of the objects, you're kind of conjugating. So this acts here in a funny way by conjugation on kind of adjacent things. So all in all, these are not the same cyclic object, but we see that the realization of this guy S bullet Bg is obtained from the realization of bar sig G by taking orbits under the realization of another cyclic object. And now I'm just going to draw this as a simplicial object because we're only going to be interested in the realization of this. Right? So this is again going to have n copies of G in like cyclic level n. So n plus 1 copies of G in like simplicial level n. So it's going to look like this. And from the fact that these copies of G here kind of remembered how the natural isomorphisms acted. And the structure maps, which I haven't explained that, but the structure maps kind of come from forgetting one object and taking a composite, similar to the nerve. You can see that the maps here are really just projections. Right? So you can, for every, and the degeneracy maps are suitable diagonals. Right? So that's not even using the group structure on G anymore. It's really just something you can do for every pointed space. Right? You can just, or for every space, I guess. You can just project, like the boundary maps simply project away one factor, and the degeneracy maps give you like a diagonal. And so the claim is the realization of this guy is contractible. And I want to pose this as another exercise. So think about what you get if you write down this kind of simplicial diagram where all the boundary maps are simply projections that project away one of the factors. Check that this really has contractible realization. Right? So even though these guys do not agree as cyclic objects, the canonical map between them becomes an equivalence on colimits, on the realizations. So that's nice. That means that we can replace this guy over here with this kind of realization of cyclic nerve that we saw over here. And what is this guy? Well, level-wise, Fun Sn into Bg, since the target is a groupoid, this is the same as just maps from the Kant complex generated by this infinity category Sn. So I'm going to write that as geometric realization here into this. And if you turn this into a Kant complex, if you turn this into a groupoid by inverting all the morphisms, then what happens is all the objects become isomorphic. And before, every object had endomorphisms given by natural numbers generated by the composite all the way around. So in this case, this guy is going to become just Bz. Right? The natural numbers, if you invert the generator, it does become a copy of the integers. So this guy actually realizes to Bz. I guess a more geometric way of thinking about it is if you take this diagram and you just really take 0 simplices and 1 simplices, you get something that's equivalent, like weakly homotopy equivalent to S1. So all of these guys are really map S1 Bg. And this is, of course, by definition, just the free loop space. Right? So the trick here is this cyclic diagram here, since we map into a groupoid, it's actually already constant. So the colimit is simply that space. Another thing you can get from this identification on the level of cyclic objects that we just made is, of course, the cyclotomic structure. And so here's the two statements. So first of all, the T action on THH S adjoint G, i.e. sigma infinity plus LBG, comes from the T action on LBG given by sort of rotating loops. Right? Or a more technical way of saying this is maps from S1 to BG, and I of course have a T action on S1, right? Just the free S1 action on S1. So that gives you an action on maps from this guy to BG, and you can use that here. So that's, I claim, the action that shows up. And then the Frobenius, sigma infinity plus LBG to sigma infinity plus LBG TCP, that actually comes with a Frobenius lift. So this admits a lift sigma infinity plus LBG to sigma infinity plus LBG HCP coming from the CP equivariant, or I guess CP invariant map from LBG to LBG, which is precomposing with a degree P map from S1 to S1. Right. You can see that that's CP invariant under the CP action by like rotating with roots of unity on the target, and so it's still invariant like this after taking sigma infinity, so it doesn't just give you a map like this, it gives you a map into the homotopy fixed points. The claim is that's our Frobenius lift. And I don't want to go into the details of these identifications, but the idea is that you can describe these things in terms of the cyclic object I just described, the cyclic nerve. And so the T action, you kind of see that appear because the part of the cyclic structure are the Cn actions in level n. And in the cyclic nerve, the Cn action is given by rotating this category Sn by like one step. And under this geometric realization that occurred, that corresponds to rotating the circle by 1/n. And so these fit together to describe kind of the S1 action on the circle itself. And then by mapping out of it, this gives you the S1 action on LBG that I described here. And the other thing is that from the description of the cyclic object, you can get the Frobenius by taking like the Tate a variant of the Tate diagonal level-wise into some subdivision. And the fact that you have this Frobenius lift that admits this very geometric description here is that the Tate diagonal, so it's kind of the key insight for this is that the Tate diagonal from SG to the p-fold tensor power on SG and then Tate CP lifts through the actual diagonal from G to G cross P. Right? You have this map. It is CP invariant. Under suspending, under sigma infinity plus, it gives you a map from SG to this p-fold tensor power of SG. And since it was invariant, it gives you a map into the homotopy fixed points. And the claim is that that factors the Tate diagonal. And so what happens is that you do this level-wise on the cyclic object that we just described. And from that, you can identify this map. I'll not go into the details. Let me put like a square in parentheses here. But again, the details are in I think section 4 of the Nikolaus-Scholze paper. Right, and so the Frobenius lift story allows us to now also describe TC of this kind of ring as a nice pullback. But there's one kind of mysterious thing appearing there, right? In the bottom, we had this map from X to X, which was like psi p minus the identity. And we still have these free loop spaces appearing. So it turns out in this setting, under additional assumptions, we can further simplify this. And this is the following proposition. So this idea comes out of a paper of 6 authors, Böckstedt, Carlson, Cohen, Goodwillie, Shang, and Madsen, where they discuss like, the relationship between TC and A theory. They focus on simply connected spaces. So under taking loop spaces, this would correspond to the setting where pi 0 of G is trivial. I'm going to do something slightly more general, but it's basically the same methods. So for G, an E1 group with pi 0 of G, a P group. The claim is that this map, psi p minus the identity, and this psi p, by what we said over here, that's really the map that just precomposes a free loop with the degree p map. So this fits into a square like this, where the vertical maps simply evaluate at the base point. If you think of S1 as kind of unit complex numbers, then the base point would be 1, and so I'm writing this as evaluation 1. Right, so this takes free loops, 2 points in here, and of course, if you precompose with the degree p map on S1, that map takes the base point to the base point. So that map is simply going to leave the evaluation at 1 fixed. So you have this commutative diagram, and down here you really have identity minus identity, i.e. 0. So the claim is that this is a pullback after p completion. Right. So let's try to see how we can check that. And the first idea is in spectra, since you're stable, a square like this is a pullback or push-out diagram, if and only if the map induced on like the cofibers of the horizontal maps is an equivalence. In this case, is an equivalent, like pullback after P completion, if and only if the map is an equivalence after P completing the cofibers. So what's the cofiber of this kind of difference between an endomorphism and the identity? Well, an endomorphism defines for you an action of the natural numbers, and co-equalizing that with the identity is the same as taking homotopy orbits under that action. So the cofibers of the horizontal maps are given by sigma infinity plus LBG, and then homotopy orbits under the action by the natural numbers given by psi p and the identity in that case. So let me put this directly below. And here's a fun thing you can do, which is the homotopy orbits under an action by n, they don't change if you first invert your endomorphism. And then, once this endomorphism is invertible, it's the same as taking homotopy orbits under the z action you get, right? So you can also write this as sigma infinity plus, let me pull out the sigma infinity because all this co-limits. So this is sigma infinity plus psi p inverted LBG, and then homotopy orbits under the z action given by the now invertible morphism. Right? And by inverting a morphism, I really mean you just take the kind of telescope, right? You take the diagram given by index over the natural numbers, it's just copies of your object and the endomorphism, and then you take the filtered co-limit there. And that guy is still going to have your endomorphism acting, but now it's invertible by construction. And the claim is that that doesn't change the homotopy orbits, and furthermore, since the action is now by an invertible thing, it's the same as a z action, and the homotopy orbits are the same. And I can do the same thing on the bottom, and there it's already invertible, right? The identity is invertible, and so here this is just the same as taking BG and homotopy orbits under the trivial z action. Right. So what do we learn from this? Well, we learn from this that it's sufficient to check that psi p inverted LBG, this kind of telescope thing, this maps down to BG, that this is an FP homology equivalence. Because afterwards we take sigma infinity, that doesn't change homology, so then the map after sigma infinity will be a homology equivalence, and we saw that for connective spectra, a map is an equivalence after P completion if and only if it's an equivalence on mod P homology. So this would be sufficient. And here we're in spaces, so we can also involve fiber sequences in spaces. So what do I mean by that? Well, look at the sequence of fiber sequences, where here we have LBG, LBG, LBG. Down here we have BG. These maps are evaluation at the base point. These maps are the identity. And these maps are psi p, precomposition with a degree p map. And so what's the fiber here? Well, the fiber is the space of based loops. And based loops on BG is just G, right? So these spaces up here, the fibers are equivalent to G. And on based loops, I still have this precomposition by a degree P map. And what does this do on G? Well, on G, it's literally the map multiplication by P, right? The map that uses the group structure to raise an element to the pth power. Note that this is only a map of spaces, not of groups, since G might be non-abelian, right? But I still have these perfectly fine maps of spaces. And so we here have this sequence of fiber sequences. And so in the colimit, we get a fiber sequence where the colimit down here is still BG. The colimit down here is what I called psi p inverse LBG. And the colimit up here, let me call this P inverse G, but keep in mind this is not something that happens in the world of groups. This is really the filtered colimit of like pth power maps on spaces. So this looks more algebraic than it is. Right. And so, right, so all we've used here is that filtered colimits commute with pullbacks. This tells you that the fiber of this map here is still P inverse G. And now we need to check that this is an FP homology equivalence. By the Serre spectral sequence, it suffices to check that this guy has vanishing FP homology. And the first thing we observe is this guy is actually the same as the thing we get if we just invert the degree P map on G0, the unit connected component of G. Why is that? Well, this is where it is crucial that pi 0 G is a P group. So basically, this tells you that even if you start with an element of a different connected component, after applying finitely many of these pth power maps, you land in G0. Right. By the way, P group here doesn't necessarily mean finite, but it means that every element is P power torsion. So that guarantees what I just told you, that somehow every element, and more generally every finite subspace or something, lands in G0 after finitely many steps. So there's some cofinality thing going on. Right. And so what's left to do is to compute for a connected group the mod P homology of applying these pth power maps. And here's the ingredient. So homology of G0 is a connected Hopf algebra. Multiplication comes from the group multiplication, and co-multiplication comes from the diagonal. And in particular, this degree P, this multiplication by P map induces not necessarily multiplication by P on homology, but it induces the map you get by taking like the P-fold Hopf algebra diagonal and then the P-fold multiplication. Right, so this is basically just using the fact that we can write the multiplication by P map as a composite on, like using the diagonal on spaces and then the multiplication, like the group multiplication, the group structure. Right, and so here's the crucial claim. This map is not necessarily zero. This is still FP coefficients, but this map is not necessarily 0, but this map is degree-wise nilpotent. And I want to pose this as another fun exercise. You have to play around a little bit with Hopf algebras, but it's not too hard. Try to proceed kind of by induction on degrees to see what's going on. Right. Using this fact, you see that taking the filtered colimit of these maps actually gives you something with 0 homology. And so by the Serre spectral sequence, this map was an equivalence in FP homology, and then what we said over here implies the claim. All right, so finally, I want to state the result that we now proved, taking all of today's results together, which is that for G, an E1 group with pi 0 G AP group TC of the P-completed guy. So let me use this notation that we introduced, which is like coefficients in the P-adix. This just means that you P-complete everything. This is, well, let me first give you the pullback because I think it's kind of easier to digest. This is a pullback of sigma infinity plus BG, P completed, sigma infinity plus BG, P completed. Here the 0 map, and here sigma infinity plus LBG, and then shifted and homotopy orbits. And this map here is this transfer map we had earlier, like norm followed by the forgetful map from homotopy fixed points to the underlying spectrum, and then further followed by the evaluation map from free loop space to like evaluating to points in your space BG. And I guess here we also need to P-complete. Maybe it would have been cleaner if I said it's a pullback after P-completion. But anyways, this is a pullback, and in particular, you get this nice formula. As sigma infinity plus BG plus, and then here you get the fiber of sigma infinity plus LBG lower HT, and then I'm going to write out this composite. So this is first take the transfer to sigma infinity plus LBG, right? That is norm and then forgetting, and then you take the evaluation at 1 to get to sigma infinity plus BG. Right, so it has this nice sum decomposition, and then I guess I want to P-complete the whole thing. All right. And that is everything I wanted to say today. Thank you all for watching, and see you next time.